All right, so this chapter is going to be on Gauss law. Gauss law. Gauss is a German mathematician. But before I discuss this law, I want to say something about area. So let's talk a little bit about area. Do you think area is a scalar or a vector? Hmm?
It can be represented as vector.
Yeah, the reason is, you see, area has this area and this area are not the same because this one is facing this way, this one is facing this way, okay? So area has directional properties, okay? So area is a vector. So area is a vector. So obviously its magnitude is the area of the surface, okay? Its direction is taken to be perpendicular to the surface of the area, okay? So its magnitude is simply the area, okay? Its magnitude is the area, and the direction is perpendicular to the surface. Direction is perpendicularly out of the surface, You see, there are two perpendicular directions. It could be perpendicularly out, or it could be perpendicularly in, right? So the direction of area is perpendicularly out. Do you remember these directions? Cross stands for perpendicularly in, okay? Cross means the direction is perpendicularly in, and dot means perpendicularly out. So the direction of area is always taken to be perpendicularly out. It's usually the direction pointing towards you. If you're not sure what it is, you put your fingers in a counterclockwise direction like this, and then the direction of thumb will give you the direction of area, okay? If you're not sure, it's usually perpendicularly out. Usually when dealing with closed surfaces, like we're going to do in this chapter, it's usually perpendicularly out, normal from the surface, okay? But if you're not sure, just use the right hand rule. If you put your fingers like this, thumb will give you the direction of the area, okay? So area is a vector quantity. It's magnitude of the area, and its direction is okay. All right. Okay. Now let me give you the mathematical definition of area. Suppose you've got this parallelogram over here. Let's say this is A. Maybe let me put A over here. Let's say this is A. This is B. Okay. So this is the area we're talking about. The area of this parallelogram is defined to be A cross B. This one is defined to be A cross B. It is a cross product between these two sides over here. We're talking about the area of this parallelogram over here is taken to be A cross B. This cross product must be done in a counterclockwise direction. You see, if you put this in a counterclockwise direction, you remember the screw rule? If you rotate a screw in a counterclockwise direction, the spring comes out, okay? So the direction of area is always perpendicularly out, and its magnitude, remember? The magnitude is what's the magnitude of cross product? If this angle is theta over here, what's the formula for the magnitude of cross product? Do you remember? It is
is AB cosine of an angle?
Yeah, cosine is dot product, but
sine.
Sine of theta, okay?
Sorry.
Now you see, if you see the formula for the area of parallelogram, if this is B sine theta, okay? And the A times B sine theta basically represents the area. So this is the area of the parallelogram. So you see this formula represents the direction and the magnitude of the area. But I have to say this has to be done in a counterclockwise direction. There are two kinds of cross product. You can say B cross A, but the direction that was going to be downward, okay? A cross B is perpendicularly out. So this is in a counterclockwise direction. You have to pick the cross product in a counterclockwise direction so that you get perpendicularly out, okay? So that is area. All right. Now, maybe let's look at some examples. Suppose we have this box over here like this. Okay, and then maybe this is my z-axis over here. This is my x-axis over here. This is my z, and this is, let's say, my y-axis over here. Okay, so can you tell me the direction of this area over here? It should be perpendicular to the surface. So what's the direction of this area over here? It's in the z direction, right? So this one should be K, you see? The z-axis perpendicular to the surface over here. So the direction of this one is K. The direction of the surface is K. This is the y-axis. So what do you think is the direction of this area over here? You see?
X.
J.
This is y. So this is the direction of y, right? So what's the unit vector perpendicular to the surface over here?
J.
X.
It's going to be j, okay? So the direction of this area is going to be j. Remember, this is my x-axis, this is my y-axis, this is my z-axis. How about if I take this area over here? What do you think is the direction of that area? You see this is x-axis? So
I.
I, very good, it's going to be I. If you take the area on this side, remember for a closed surface, it's always perpendicularly out. So the direction of this surface, this is j, but this one is going to be negative j, okay? So the direction of this area over here is going to be negative j. The direction of the bottom surface is going to be negative k, okay? And then this surface over here is direction going to be negative I. So the direction of area is always perpendicular to the surface, and the magnitude is the area of the surface, okay?
So the direction goes in the same direction as the force if we were calculating for an object hitting it.
No, force has nothing to do with it. It's just perpendicular to the surface. We're not talking about force. You take the surface, the direction perpendicular to it is the direction of the area, okay? In a perpendicularly out direction. There are two kinds of directions, perpendicularly in and perpendicularly out. The direction of the area is always perpendicularly out, okay? So it has nothing to do with force. It has to do with the surface, the direction of the surface. It is perpendicular to the surface, okay? So Gauss law is based on electric flux. So let's talk about electric flux. Electric flux is a measure of the amount of electric field that crosses the surface perpendicularly. This is a measure of the amount of electric field, that crosses a surface perpendicularly, that crosses a surface perpendicularly, okay? So let's say you have this surface over here, and you have this electric field crossing it like this, let's say, okay? So the electric flux, this has two components, a direction parallel to the surface, a direction perpendicular to the surface. The direction parallel to the surface doesn't contribute anything to the flux. We're looking only at the electric field that crosses perpendicularly. So you take this component over here, which is E perpendicular, you multiply by the area, that's what we call electric flux, okay? So electric field flux is proportional to the electric field. So we're going to use phi for electric flux, okay, it's phi. So this is defined to be proportional to the perpendicular component of the electric field, the component of the field not crossing it perpendicularly, and then to the area of the surface, okay? Now, the direction of area is perpendicular to the surface, okay? So this is also the direction of the area over here, it's perpendicular to the surface. So if this angle is theta over here, if this angle is theta over here, E perpendicular is the magnitude of the electric field times cosine of theta, okay? So E perpendicular is the magnitude of the electric field times cosine of theta. Do you see that? If this is the electric field and the angle between the area and the electric theta, then the perpendicular component, the component in this direction, E times cosine of theta. So this is defined to be flux is E times area times cosine of theta, okay? Now, can you write this in terms of dot product? How do you write this in terms of dot product? What's the definition of dot product?
You said dot product?
Yeah, it's a dot product. You remember? We have this
So
formula.
it'd be E dot A?
Yeah, A dot B is A times B times cosine of theta, right? So we can write this one as flux equals the dot product between the electric field and the area, okay? So that's another way of writing it. So the flux, now we're dealing with a constant electric field and a flat surface. This is obviously for a constant field. We're going to generalize later, but this one is for constant field and a flat surface. We can generalize in a minute, but this is an exception for a flat surface and a constant electric field. Okay, so this is the definition of electric flux. It's the dot product with the electric field and the area. Okay, so the flux could be positive or negative depending on the angle. If the angle is acute, then the flux will be positive, right? These are magnitudes. E is magnitude of the field, A is the area, these are two positives. The negative can come only from here. If the angle is acute, it will be positive. If the angle is 90, it will be 0. If the angle is obtuse, it will be negative. Okay, so it can be positive or negative. It's a scalar, all right? So let's look at some examples. Suppose, let's say I have this square over here. Let's say this is 2 meters. Let's say this one is 2 meters. Let's say it's a square. And the field is like this. Let's say this is E equals maybe 10 Newton per meters. Okay, what do you think is a flux crossing this surface over here? Remember, flux is the amount of electric field that crosses the surface perpendicularly. Okay, so that this field has a component perpendicular to the surface. You see, this is parallel, so we expect the flux to be 0, but let's do it mathematically. The area is a square, is 2 times 2, is 4, right? The electric field, we're told, is 10, right? Newton per coulomb. How about the angle? Remember, the direction of area is perpendicularly out. This is the direction of area, perpendicularly out. And the electric field is parallel to the surface. So what's the angle between the area and the field?
90 degrees.
90 degrees, very good. Theta is 90 degrees. That's why it's 0, okay? So the flux would be the area of the electric field, the area, and the cosine of theta. So you've got 10 for the field, 4 for the area, and then we've got cosine of 90. That's why it's 0, because cosine of 90 is 0. Okay? How about, let's say you have this circle over here. Let's say the radius is 1. Okay? And then we have this electric field, which is perpendicularly out. Okay? This is a symbol for perpendicularly out, if you remember. All right, and let's say the electric field is maybe 5. This is 1. Okay, so obviously the electric field is 5, the magnitude, okay, per coulomb, and the area is a square, so it's going to be pi times 1 squared. It's going to be pi. How about the angle? What's the angle between the area and the field in this case?
It's also 90 degrees.
It's 0 if it's perpendicular.
It's 0. Look, area is always.
Oh, yeah.
Area is a dot, it's perpendicularly out. So the field is also a dot, right? So the flux is,
Okay.
the angle is 0 in this case, okay? So the flux is going to be EA times cosine of theta, all right? So you've got the electric field is 5, the area is pi, and then we have cosine of 0. Cosine of 0 is 1, so you get 5 pi, and the flux, of course, is this is Newton per coulomb times meter squared. This is sometimes called the Weber, but it's not very common. All right. Okay. How about we have this one now? Let's say we have a rectangle over here, 1 and 4 meters over here. But this time, let's say the field is perpendicularly into the plane of the paper. Okay. So the area obviously is 1 times 4, right? That's 4 meters squared. Let's say the field is maybe 10 Newton per coulomb. Okay, we have the electric field 10 Newton per coulomb. Now, what's the angle between the area and the field? Remember, cross means perpendicularly into, okay? And area is perpendicularly out. So the area is, the field is perpendicularly into, but the area is perpendicularly out. So what's the angle between the field and the area?
180 degrees.
180, very good. In this case, it's 180 degrees, okay? 180 degrees. So you get flux is EA cosine of theta. So you've got 10, and the area is 4. Then you've got cosine of 180 degree. Cosine of 180 degree is -1, so you get -40 Newton per coulomb times meter squared, okay? So you can see flux could be negative, positive, or 0, depending on the angle between the field and the area, okay? Now, so far we've been dealing a flat surface and a constant field. Now we're going to generalize, okay? Suppose, let's say you have an irregular surface, over here. So the direction of area could be different from place to place. We're talking about curved surface, something like that, okay? So To do the flux, you have to take a small element over here. Let's call that dA, okay? And then you take the electric field on that small area element, okay? So on this small area element, the electric field can be taken to be a constant. So we can use the formula for a constant electric field, right? So we take the flux over here, it's called d phi, and that's going to be the electric field times the small area element dA, okay? And then to get the total flux, you just add up all of them, okay? So you get the total flux is the integral of E dot dA, okay? So this is the general formula for flux. If you've got the electric field and the area changing everywhere, you just take a small element, you calculate the flux for that small element, and then you add up the fluxes crossing over the all area elements, okay? So this is the formula for electric flux. This is what you call surface integral in calculus. Have you done surface integral in calculus? No, yet? So this is what you call surface integral in calculus. It's simply flux is the surface integral of electric field. Okay, so let's specialize this. If E is a constant, just to get the formula that we already got, if E is a constant and the flat surface and a flat surface, okay, so you can take E out. It's a constant, right? So you get phi equals E dot the integral of dA, and the integral of dA is the area. Okay, so if Lx was a constant, you just get the formula we've been using already, which is E dot A. Okay, so if the electric field is constant, you simply get this formula. If the electric field is a constant, and the surface is flat. Okay, so that is what we call electric flux over any surface. But in this section, we're mainly interested in the electric flux on a closed surface. So for a closed surface, let's say we've got a sphere closed surface. If you do the surface integral of a whole surface, it's written something like this. If it's a whole closed surface, you have to write it like this. This is this one over here is flux over a closed surface. This circle means flux over a closed surface. This is a symbol for flux over a closed surface. Okay? So we're going to write the symbol a lot. It means flux over a closed surface. All right? So this is a definition of flux. Now we're going to look at Gauss law. We'll look at Gauss law. Gauss law. This law says the electric flux over a closed surface is proportional to the charge, to the total charge enclosed inside that closed surface. Okay, this law says that the electric flux over a closed surface is directly proportional to the total amount of charge, enclosed inside the surface. Okay, so let's say you have this surface over here. If you calculate the flux on this irregular surface, you take a small element over here, that's dA, you take the electric further, you do E dot dA, you do that for all the surface elements and add them together, which is represented by the symbol over here. Okay, this law says this is proportional to the total amount of charge enclosed inside the surface. You've got charges Q1, Q2 over here. You have to add them, all of them, okay? Charges outside don't count, only charges inside. And this constant proportionality turns out to be 4 pi times K, okay? So this is the mathematical equation for Gauss law. If you take this surface integral over a closed surface, it equals 4 pi K times the charge enclosed inside the closed surface, okay? This is the mathematical statement of Gauss law. Okay, so if I know the charge inside, this integral is very difficult to do for this irregular shape. But if I know the charge inside, I just add up all this charge inside, and this surface integral over here is going to be 4 pi k times the charges enclosed inside. All right. So you can do surface integrals for electric field very easily using this formula. Now let me introduce you to a new constant epsilon. This the constant epsilon is equal to 1 over 4 pi k, and it's called electric permittivity of vacuum. I call electric permittivity of vacuum. Okay. Its value in calculated. Remember, k is 9 times 10 to the power of 9 in calculated, and epsilon turns out to be approximately 8.85 times 10 to the power of negative 12. Okay, so probably most of the time you'll see this formula: E dot dA equals the charge enclosed inside divided by epsilon. So that's what it means. Okay, epsilon simply means 1 over 4 pi k. So this is another way of writing this formula in terms of epsilon, or permittivity of free space. Now, we can prove this formula very easily using Gauss law, or I mean using Coulomb's law. Let's try to prove it. Let's say proof for a point charge. Proof for a point charge. Suppose this is my charge Q over here, okay? And I want to calculate the flux over a spherical surface of radius r, all right? Let's calculate this flux over here. Let's say it's the radius r, okay? What we're doing is we're going to calculate the flux over a small area element like this, okay? And then we're going to add up all of them, and then the charge Q over here, okay? So total flux is this one, E dot dA. Okay, so if I take this area element over here, you see the direction of the area is this way. This is my dA. What do you think the direction of this area is? Perpendicular to this tangent over here. Okay, remember this is the position vector from the origin to the location of the area. Okay, so what do you think is the direction of the area? It is the direction of the position vector, right? This is a position vector, and the area is supposed to be perpendicular to the surface over here, so it's going to be the direction of the position vector. So the dA is simply its magnitude dA, and then the unit vector ER, or ER equals position vector divided by the magnitude. Okay. How about the electric field? We know the electric field from Coulomb's law is K, and then you've got the charge divided by R squared in the direction of ER. You remember that? That's the formula for the electric field due to point charge. All right, it is K charge divided by the distance squared in the direction of the position vector. All right, so let's do this product now. E dot dA. Okay, the electric field is K Q over R squared in the direction of ER, and the area is dA in the direction of ER. Okay, what is ER dot ER? A unit vector dotted by itself. What does it give you? So this one is KQ over R squared times dA, and then you've got ER dotted with ER. What do you get if you dot a vector by itself? What is A dot A?
1.
No, A dot A, and I mean, this one you're right, it's 1, but A dot A would be A squared. Well, if you want, you see, this is a unit vector, right? So its magnitude is 1, and then times 1, and then since they are identical vectors, the angle of them is 0, right? So cosine of 0 is 1, so you get 1. So ER dot ER is 1, like I dot I, J dot J, or K dot K, okay? This is a unit vector, its magnitude is 1, its magnitude is 1, and then they are parallel, it's the same vector, the angle is 0, cosine of 0 is 1, you get 1, okay? So what you have is this dot product over here, E dot A, is simply K Q over R squared dA, okay? Now, let's say this surface is of radius R. All right, so R is going to be, this is representing any R, but if you're using Gaussian surface of radius R, then this R will be simply be capital R, or let's just say arbitrary R, okay? So let's do the flux now. the flux is, this is over the entire surface area, okay? E dot dA, but we just conclude that this dot product is K Q over R squared times dA, okay? Now, over the surface over here, remember, we're just dealing with this area elements over here. This is a Gaussian surface we're using, okay? So the radius is a constant. The radius doesn't change over this surface, okay? So I can take it out. Over this Gaussian surface, the radius is a constant, K, Q, they're all constants. So you've got K, Q over R squared times the integral of dA over the entire sphere, okay? So what do you think this would give me? If you add up all the dA small area elements over all the surface area of the sphere, I get the surface area, right? What's the formula for the surface area of a sphere? Do you know?
Is it 4/3 PR?
That's volume, area. It's 4 pi r squared, okay? So this one is 4 pi r squared, okay? So you get, this is K, Q over r squared times the surface area of a sphere, which is 4 pi r squared, okay? R squared goes over with r squared, and you get Gauss law, which is E dot dA equals, you see, 4 pi K times the charge enclosed, okay? So for a point charge, you can easily prove it like this, all right? All right, now let's look at some examples. Let's look at some examples, okay. Now, suppose I have, let's say, consider, let's say, a cube of size, let's say 2 meters, okay? So we have this cube over here, and the side is, each side is 2 meters, all right? And let's say this is my coordinate system over here. So let's say this is the X, let's say this is the Z, and let's say this one is my Y, okay? Now suppose we have the following electric field. Now remember, this point over here is 2, this point over here is 2, this point over here is 2, because it's a cube, okay? Suppose we have the following electric field. Let's say the electric field, let's say equals, we're gonna have 2 branches, 4 Newton per Coulomb in the I direction if, let's say, Y is greater than 1, and then let's say maybe negative 2 Newton per Coulomb in the I direction if Y is less or equal to 1, okay? So you see, 1 is from over here, okay? Okay, so if the field is in this direction, like this, if, let me put, I think it's easier to see Y. Let me change it to J. So let me change J in the Y direction, okay? So what we have is, let's say Y is over here. So we're saying the electric field for greater than 1 is in this direction over here. And the electric field for that one, for less than 1, is in this direction over here, okay? So we're saying this is for this one in the J direction, and the other one is negative 2 in the negative direction, okay? So this is 2 Newton per Coulomb. So the question is, calculate the total charge enclosed, okay? The question is, calculate the total charge enclosed, the total charge enclosed. So what do you have to do to find the total charge enclosed? Here is Coulomb's law. If you can do surface integral, then you calculate the total charge enclosed, okay? Because of this formula, this is surface integral, okay? And that equals 4 pi k times the charge enclosed, okay? So if I can calculate this surface integral over here, then I can calculate this enclosed charge from this formula, okay? So all I have to do is the surface integral of the whole surface. All right, now tell me, if I take this surface over here, what do you think the flux? What's the direction of this surface over here?
K.
K, very good. But the field is J. So what's the dot product? What is K dot J? In other words, you see, this field is parallel to the surface. It doesn't have a perpendicular component crossing it, so it's going to be 0, okay? So the area over here has a direction of K, but the field is J. If you take the dot product, you get 0. This field does not have a component in the K direction, okay? So the flux over here is going to be 0. The same thing if you take the bottom surface over here. You see, the direction of the area is going to be negative K, but the field is J, so you still get a 0, okay? The field is the J direction. I'm talking about this surface now, the bottom surface over here, okay? So the area is in the negative K direction over here. The field is J, so you get 0, all right? How about on this surface over here? Let's look at this surface now. What's the direction of this surface over here? This is X. What's the direction of this surface over here?
I.
I, very good. But the field is J. They're both J, okay? So what is I dot J? Remember, if two unit vectors
Is it 1?
No, unit vectors, if you dot by itself, it's 1. If you dot two different unit vectors, it's 0 because they're perpendicular to each other, okay? Cosine of 90 is 0. I and J are perpendicular to each other. So the angle is 90, so you get cosine of 90. So the general rule is, if you've got A dot A, J dot J, or K dot K, that's 1. But if you've got different ones, A dot J, or I dot K, or J dot K, they're all 0, okay? So if you're dotting different unit vectors, it is 0 because they're perpendicular to each other. But if you're dotting a unit vector by itself, it's 1, okay? So over here, you have the direction of the area is I, but the field is J, you get 0. The same thing if you talk about this surface over here, you see? The direction of this surface over here is negative I, but the field is J. So you get 0 too. The only surface you're going to get a contribution are these two. This one and this one over here, because the direction of this areas are in the J direction. Okay? So for this one, what do you think the flux? The electric field is 4 in the J. What's the direction of the area over here? It's J, right? So for that one, first, let's do the electric field. The electric field, I hope I gave them, let me just surface, let me give this names. Let me go this A, let me go this B. This is surfaces, all the others are 0, okay? So let's say this is flux on surface A plus flux on surface B, okay? So for this one, for this surface over here, it is greater than 1, the electric field is 4, okay? So the electric field is 4, and that is the J direction, okay? This is the electric field. That with the area. The area of this one, remember the side of the cube is 2, 2 times 2, that's 4, right? The area is 4, and the direction is also J, okay? The direction of this area over here is J, okay? So they're both J. So J dot J, this would be 16, and then J dot J, which is 1, okay? This is 1. So you get 16, this is Newton per Coulomb times meter squared, okay? So this is the flux crossing this surface. How about, maybe let me say phi A over here, okay? How about phi B, okay? That is y less or equal to 1. Now I'm talking about this surface over here, okay? The electric field is 2 in the negative J direction, right? So the electric field is negative 2 in the J direction. How about the area? The area is 4. Now what do you think is the direction of this area over here? Can you tell me?
Negative J.
Negative J, very good. It has to be, for a closed surface, the direction is always the outward normal, okay? So the direction is negative J, all right? So this is 4 in the negative J, all right? So you do the integral, negative times negative 4 is 8. 8 J dot J is, J dot J is 1, so you just get 8, right? So it's Newton per Coulomb times meter squared. So the total flux, you see, crossing this cube, all the others are 0 except these two, and these two are 16 plus 8, that is 24. Okay, now I go back to this equation now. You see, that equals 4 pi k times the charge enclosed inside. Okay, and so I get the charge enclosed inside is 24 divided by 4 pi times k. Okay, that is 24 divided by 4 pi, and k is 9 times 10 to the power of -9. That's a lot of charge. It doesn't make sense, but it's mathematically correct. Okay, so you see, what do you calculate the enclosed charge? We just calculate the flux over the total surface, and then from this formula, we can find out how much charge is enclosed inside. Do you see that? Do you have any questions on this formula? No? Okay. Another example. Okay, suppose I have the following cylinder over here like this. This cylinder over here. So let's say this is my coordinate system. Let's say this is the y-axis. Okay, so this is y, this is x, this is z. Okay, let's say the radius of this one is maybe 1 meters. Okay, so the radius is 1 meters. Let's say the length is maybe 10 meters. That's the length of the cylinder. All right. Now, suppose we have the following electric field. The electric field, let's say, is 8, let's say Newton per Coulomb. Let's say in the j direction. If this is the x-axis, let's say y is greater than 0, and let's say equals maybe 2 Newton per Coulomb in the negative j direction. Maybe let's say positive j direction. Positive j direction if y is less than 0. Okay, so what do we have? If it is greater than 0, the electric field over here is 8 in the j direction. Okay, but for less than 0, it is in this direction, and that is still, oh, that's still in the j direction. In the j direction, so it's 2 in the j direction. Okay, so for greater than 0, the field is 8. For less than 0, it's still to the right, but it's 2. Okay, so the question is calculate the total charge enclosed. Okay, so the question is calculate the total charge enclosed. Okay, so once again, we're going to do the surface area of the closed surface. You've got 2 end faces. Let's call this left end, right end, and a curved surface. Okay, so we can say that this integral over here, electric field, that A, this is a flux with the entire surface. I can divide it into 3 parts. I've got a curved surface. Okay, so I can say this is E dot dA on the curved surface. Okay, and then I can do it, there is a left end over here, so I can do this over the left end, and then I've got the right end over here. Okay, the integral of E dot dA over the left end. Okay, so I divide in 3 parts: the curved surface, the left end, and the right end. So let's do this 3 parts. Look, on the curved surface, the direction is going to be perpendicular to the y-axis. You see, you take a tangent to the curved surface, the area should be perpendicular to that one. So over all this surface elements of a sphere, the direction is going to be perpendicular to the y-axis. Okay, so you can say E in the direction of R perpendicular. If this is the cylinder, then the area is perpendicular everywhere, perpendicular to the surface everywhere. Okay, but the field everywhere is parallel to the curve. Do you see that? So what do you think the flux would be if the field is parallel to the surface?
0.
The field is parallel, the area is perpendicular to the field, so it's going to be 0, okay? So on the curved surface, it's going to be 0 because the direction of the area is perpendicular to the surface, okay? So this integral over here, curved surface, I should put a circle, this E dot dA on the curved surface is going to be 0 because E is perpendicular to area. Okay, so you don't worry about that. Over the entire curved surface, the field and the area are perpendicular to each other. Okay, so the flux is going to be 0 because of that. Perpendicular means 90 degree, cosine of 90 is 0. We have contribution only from these two, from the left end and the right end. So let's look at those two ends. So let's look at E dot dA on the left end. Okay, now the electric field is constant, so you can say this is simply the electric field dotted with the area. Okay, now for less than 0, we're told the field is 2 in the j direction. Okay, the field is 2 in the j direction, we're told over here. Okay, for less than 0, it is 2 in the j direction. What is the direction of the area on this end? What's the direction of the surface over here?
Negative J.
Negative j, very good. So this is negative j, and the area is circular, it's going to be pi r squared, okay? So the area is going to be pi times 1 squared, and the direction is negative j, okay? So we get negative 2 pi, and then you've got j dot j, which is 1, okay? So you get 1 over here, so that's negative 2 pi, all right? So that is the flux on this end. The reason it's negative is the area is this way, but the field is this way. That's why it's negative, okay? All right, so that's the left end. Now let's do the right end. E dot A, the right end, okay? And then the electric field is a constant. The surface is flat, so we can just say this is E dot dA, okay? Now, on the right side, we're told the field is 8 in the J, okay? On the right side, the field is 8 in the J. The area is still pi r squared, circular, okay? But what's the direction? What's the direction of the surface over here?
J.
J, you see? It's the outward normal, so it's going to be J. So this surface, this unit vector is J. So we get 8 pi J dot J, which is 1. Okay, this is 1, so you get 8 pi. Okay, so the total surface area, the total flux crossing this this cylinder is 0 for the curved surface, negative 2 pi for the left end, and then 8 pi for the right end. Okay, that gives you 6 pi. Okay, according to Gauss law, that equals 4 pi times k times the charge enclosed. Okay, so the charge enclosed, so the total charge enclosed is 6 pi divided by 4 pi k. Okay, so you've got 6 over 4 or 3 over 2k coulombs. All right, so this will be the total charge enclosed inside the cylinder. So all you have to do is calculate the flux, and from there you calculate the total charge enclosed. Okay. Now let's look at another example. Suppose I have these charges. Let's say I've got this is Q1 equals 2 nanocoulomb. I've got Q2 equals negative 3 nanocoulomb. Maybe I have Q3 equals 4 nanocoulomb. I've got another one. Let's say Q4 equals negative 5 nanocoulomb, and so on. Okay. Now I want to calculate the electric flux crossing the surface. Okay, it's a very irregular surface. I want to calculate the electric flux across this closed surface. Okay, so the question is calculate the electric flux crossing, the electric flux over the closed surface, Okay, this is three-dimensional surface. I'm just simplifying. Okay, all right. How do you think I'll go about it? That's the question. Calculate this one for the surface. E dot dA. That's what I have to find. I have to find the total flux crossing the surface. How do you think I'll calculate it?
Sum of the charges first.
Yeah, this is, I know that from Gauss law, this surface integral over here, you see, if you take dA over here, this is my dA over here, and then you take the electric field over there, you do A dot dA, you do that for all of them and add them together, that's what this represents. But Gauss law tells me that is 4 pi K times charge enclosed, total charge enclosed. What's the charge enclosed? You see, these are charges enclosed. 1, 2, 3. This is not enclosed. Okay, so the Q enclosed, I have this one, is Q1 plus Q4. I've got Q3, except Q2, the 4 charges, right? Q1, Q3, Q2. Okay, so I have to add these 3 charges. This is not inside, so it doesn't count. All right, so we add them together. This is 2. This is the 4. Okay, 6, and 6 minus 5 is 1. Okay, so we get 1 nanocoulomb or 10 to the power of -9 coulomb. Okay, you see that? We've got 2 over here, plus 46, minus 5 is 1. That is 1 nanocoulomb, that's 10 to the power of -9 coulomb. Okay, so from that I can calculate the flux now. Okay, so I have now, so I can say this flux over here, E dot dA, for this irregular surface is 4 pi K times the enclosed charge, which is 10 to the power of, maybe let me add them together over here. We have, put them over here. Q1 is Q1, Q4, Q3. This is Q1 plus Q3 plus Q4. Okay, and that is 4 pi, and this is 9 times 10 to the power of 9. You remember that? And this, you add them, you get 10 to the power of -9. Okay, so you get 4 pi times 9. That is 36 pi. Okay, so that's the flux. All right, so this surface integral is very difficult to do, but if you know the charge enclosed inside, you can do surface integral very easily. Okay, now let's look at another example. Suppose the electric field is given by the following formula. Let's say the electric in a certain region is E equals, let's say maybe 2 times 10 power -6 divided by the radius squared. Okay, so you have a certain origin. This is this one respect to origin. This is the how the electric field varies. All right, and the direction is in the direction of the unit vector. Okay, so this is my origin over here. The electric field is going like this, is the direction of ER. Okay, this is the electric field like this. And the direction of the position vector, any point will be the direction of the position vector. Okay, so the question is, calculate the total charge enclosed inside a spherical surface of radius 2 meters, let's say centered at the origin. Okay, so now we have the electric field. We want to calculate the amount of flux, the amount of charge inside this surface over here, and its radius is 2 meters. Okay, So this distance over here is 2 meters. All right. So once again, we have to use Gauss law, right? The total flux over here, E dot dA, for this Gaussian surface equals 4 pi k times the charge enclosed. Okay, so that what I have to do is this charge enclosed is 1 over 4 pi k times this surface integral on the spherical surface. Okay, so I'll have to just calculate this one. All right, so how do we calculate this one? We take an arbitrary area element over here. Okay, we divide in small area elements. You see this, the dA is going to be perpendicular to this one over here, right? So what's the direction of the area over here? Can you tell me? The direction is in the direction position vector. Do you see that? This is my position vector. So the direction of area is in the direction position vector, which is dA in the direction of ER. All right. So I have the electric field. This is the electric field over here. Okay. And I have the area element. This is a small area element dA, and its direction is also in direction position vector. At any point, take over here is going to be the direction position vector. So this is the unit vector, the direction position vector. All right. So let's do this first. What is E dot dA? E dot dA is the electric field is 2 times 10 to the power negative 6 divided by r squared in the direction of ER, right? How about the area? The area, this is dotted with the area, take small area element, that's also in the direction of ER, okay? Both the electric field and the area are in the direction of position vector. Do you see that? Do you know why this is in the direction of position vector? It has to be perpendicular to the surface element, and the position vector is perpendicular to that position element. That's why the direction position element, okay? So this is, you see ER dot ER is now 1. So you just get this one, 2 times 10 to the power negative 6 divided by r squared dA. And ER dot ER is 1. All right. What's the value of R on the surface? Now, remember, we're doing the integral on this surface. So R is constant. What's the value of R? The radius, 2 meters. Okay. So R is 2 meters. R equals 2 meters on the surface. 2 meters on the surface of the sphere. Okay. So this E dot dA is 2 times 10 to the power negative 6 divided by 2 squared dA. Okay. Now let's do the integral. This integral E dot dA over here is this one. You've got 2 times 10 to the power negative 6 divided by 4 times dA, and then the surface, the integral down to the surface. Okay. So this is 0.5 times 10 to the power negative 6. Okay. And then you've got the integral of dA. What do you get if you integrate dA over the entire surface? If you add all the small area elements, what do you get? You get surface area, right? And that is surface area of a sphere. What is surface area of a sphere? 4 pi?
4 pi r squared.
R squared, yeah. So this one over here, dA is simply 4 pi times the radius squared, okay? So this is 4, that's going to be 16 pi, okay? So you see, so this integral over here is simply this one. We have 16 pi times 0.5 is going to be 8 pi. So that is 8 pi times 10 to the power of negative 6. All right. And that equals 4 pi times the charge enclosed inside. Okay. So the charge enclosed inside, is 8 pi times 10 to the power negative 6 divided by 4 pi. Okay, so this is the total amount of charge enclosed inside the spherical surface. Okay, so let me go through it again. We're told what the electric field looks like. Its magnitude is this one, and its direction is ER, which means it's in the direction of the position vector. Okay, and we're told to calculate the total amount of charge enclosed inside this surface. Okay, so we have the electric field. We got to get the area element to integrate. Okay, so you take any area element over here. Its direction is a direction position vector because it's sphere. Okay, that is a TA, and ER is a unit vector and the direction position vector. Okay, so as the direction of the electric field and the direction of the area are the same everywhere. They're parallel. Okay, that's why you get ER dot ER1 over here. Okay, so once you have the surface integral, then just use Gauss law to get the charge enclosed. Okay. All right, I think let's take 5-minute break and we'll continue the next one. Okay.
Thank you.
All right, I'll see you in 5 minutes. All right, the next section is going to be on applications of Gauss law. Applications of Gauss law. This law is usually used to find formulas for the electric field due to symmetric charge distributions. Okay, this one helps you to get electric field of symmetric charge distributions. Helps you to get electric field of symmetric charge distributions. Symmetric charge distributions. Okay, usually the calculation of electric field is a very complex integral, but using this this law, you can obtain electric field due to symmetric charge distributions very easily. So we're going to look at a number of symmetric charge distributions. Okay, let me start first with electric field due to point charge. We already know the formula already. It's kq over r squared, but we're going to start with that one so that you can see how it works. Electric field due to a point charge. Okay, so we have this charge over here. Let's say that's Q. Okay, now we have to select our Gaussian surface in a way that we can take advantage of symmetry. All right, so in this case, a very suitable surface is a spherical surface enclosing this charge. Okay, so if you take a spherical surface of radius r enclosing this charge. Okay, let's say we're looking at this point. This distance, let's say, is r over here. Okay, now first we're going to make some conclusions from symmetry. Okay, symmetry conclusions. Symmetry conclusions. You can make this kind of conclusions when all the points are subjected to the same condition. Okay, now since these all points are at the same distance from the charge, from symmetry you can assume that the electric field is constant over the spherical surface. Okay, so this is my Gaussian surface. You can use any Gaussian surface, but you have to choose it in such a way that you can take advantage of symmetry. Okay, if I don't select spherical surface over here, I cannot say the electric field is constant on the spherical surface. Okay, so the first conclusion I can make is the electric field is constant on the spherical surface because they're all same distance from the charge. They're all subject to the same conditions. Okay, so I'll say the electric field is constant over the entire surface, over the Gaussian surface. Okay, so that's my first conclusion. So what I'm saying is the magnitude E is a constant because they're all at the same distance. Okay, now let's look at what conclusion we can make about the symmetry. Now you see, if I want to calculate the electric field over here, I have to add up this electric field over here. You see, it can only be in this direction, the direction position vector. Okay, you see that? If I take anywhere over here, the direction can only be this way, and so on. So the direction is in the direction of position vector. Okay, so another conclusion I can make from symmetry is that the direction of the electric field is in the direction of position vector. In other words, this direction is ER. Okay, remember ER? ER is position vector divided by the radius. Okay, so the direction from symmetry is in the direction of the position vector. All right, so the second conclusion is direction at any point on the surface is in the direction of the position vector, in the direction of the position vector, that's ER. Okay, so direction of the electric field in the direction of position vector. So what do I know so far? The electric field, its magnitude constant E, and its direction is the direction of position vector. So I've made this conclusion just from symmetry. Okay, all right, okay. Now let's look at the area. Remember, we need both area and electric field to do the surface integral. Okay, so if I take this area element over here, remember the direction of area is perpendicular to the surface. Okay, and it's the outward normal. So it's going to be perpendicular to over here. If it is perpendicular to this tangential element over here, it's going to be in the direction position vector. Okay, so the direction of the area is also in the direction of position vector. Okay, so this is dA equals dA in the direction of ER. Okay, so I've got this conclusion for a spherical surface element. I've got dA, its magnitude dA, and then its direction is also in the direction of the position vector. Okay, so what does it mean? If you do this integral over here, I mean this product over here, you get E in the direction of ER dotted with dA in the direction of ER. Okay, so that is E dA and then ER dotted with ER. A unit vector dotted by itself is 1, right? Like I dot I, j dot j. So this is 1. So you get this is E dA. Okay, so now let's go to the integral over the closed surface. Okay, that is just EdA. All right, but we said the electric field is a constant, right? Because of symmetry. So I can take this electric field out. Okay, so I've got E and then the integral of dA. If I add up all the small area elements of the entire surface area, what do I get? I get surface area of the sphere, right? And the surface area of the sphere is 4 pi r squared. 4 pi r squared, right? So this integral over here is E times 4 pi times the radius squared. Okay, but from Gauss law, we know that this equals 4 pi k times the charge enclosed. In this case, the charge enclosed is a point charge q. Okay, so the electric field is this one, is 4 pi k q divided by 4 pi r squared. You see that? So the 4 pi goes out, you get k q over r squared. Okay, and then we have already said from symmetry the direction is in the direction position vector, right? So we get the electric field is kq over r squared in the direction of the position vector. Okay, so we derived Coulomb's law using Gauss law. This is it. We're able to get a formula for the electric field using Gauss law. And as you remember, this is position vector divided by its magnitude. So you can also say this is kq over r cubed times the position vector in terms of position vector. Okay, so we derived Coulomb's law using Gauss law. All right. Now, if you know this point over here, let's say is x, y, z, how do you calculate the unit vector? Can you tell me? If this point is x, y, z, how do you obtain the unit vector at this location over here, ER? Okay, let me see. So ER from coordinates, because sometimes you may be asked to calculate certain points. Well, this is like this. ER is position vector divided by R, right? R is simply the coordinates, x, y, z, right? And R is square root of x squared plus y squared plus z squared, okay? So if you know the coordinates of the point, at any point, you can calculate this unit vector as R divided by R. This is x in the I plus y in the j plus z in the k divided by square root of x squared plus y squared plus z squared, okay? So if you're asked to find this direction at a certain point on the sphere, if you know the coordinates of the point, you can calculate the unit vector using this formula, okay? All right, now we're going to look at electric field due to a spherical charge. Electric field due to a uniformly charged sphere, okay? So in this case, we have the following. We had a point before, but now we have a sphere, which is uniformly charged, okay? Let's assume it's positively charged. So this is uniformly charged like this, all right? And so we want to find a formula for the electric field everywhere using this symmetric charge distribution. Symmetric because it is spherical, okay? So we're going to get different formulas outside and inside. So I'm going to separate the problem into two, okay? Let's say the radius of this one is R, okay? So case one, let me put it right over here. Case one, I'm going to look for points which are outside the sphere or are greater than the radius, okay? I want to obtain the electric field maybe somewhere over here, okay? Now take advantage of symmetry. I'm going to take my Gaussian surface to be a spherical surface concentric with the sphere. Take advantage of symmetry, okay? So now what I'm saying is this is the radius. This is a point at which I'm trying to calculate the electric field, okay? So to take advantage of symmetry, I'm going to take my Gaussian surface to be a spherical surface of radius r. So it's going to be my spherical surface, okay? This is going to be my spherical surface. All right. So what conclusions can we make from symmetry? Conclusions, symmetry conclusions. Symmetry conclusions. Okay. Let's look at the magnitude of the electric field over here. Do you expect the magnitude to be the same everywhere over here? You see, all these points over here are subject to the same conditions. So you expect the electric field to be a constant. If you take this point, you see, you can calculate the electric field due to this one, this one, and so you're going to add up together. They're all subject to the same conditions. So you expect the electric field to be a constant on this spherical surface, okay? That is conclusion from symmetry, because they're all subject to the same conditions. When you do this integral for the electric field, you do the electric at this point, you add all of them. They're all subject to the same conditions. So the first conclusion we can make is the electric field is constant on the surface. E, the magnitude. E is constant on the surface. Constant on the Gaussian surface. Gaussian surface. Now let's look at the direction of the electric field. Okay, suppose we take this point over here. Okay, what you do normally is you take a certain element over here, you do the electric field over here, so it's going to be something like this. Okay, but I can find another symmetric charge over here that That's going to be in this direction. So this components over here, they cancel each other. You get only a direction in the direction of position vector. You see, for any point, I can find another charge that cancels the component tangent to the curve, okay? You see, take over here. If I take this one, if I take this charge over here, let's say this way, I can find another charge on this side that will go this way. So these two components cancel each other. So at any point, it's going to be radial. So the direction is in the direction of position vector everywhere from symmetry, okay? So in this case also, direction is in the direction of position vector. Direction of E is in the direction of the position vector, or ER. Position vector or ER, okay? So what we're saying is from symmetry, we have concluded this one. E equals E in the direction of ER, where E is constant on the Gaussian surface. That is our symmetry conclusions, okay? Where E is constant on the surface or on the Gaussian surface, okay? So now I can do the integral, okay? I can do the integral now. So, but to do the integral of E, let's look at dA, okay? Because I need E dot dA, right? So if you take, this is also a sphere. So what's the direction of area for a sphere? You see, it's going in the direction of the position vector, okay? You take this area element over here, is tangent to the surface of the sphere, and the area, which is supposed to be perpendicular to the surface, is going in the direction of position vector, okay? So the direction of the area in this case is the area element A, and then the direction of the position vector, okay? So I have dA over here is the area element in the direction of position vector, okay? That is both the area and the electric field have the same directions, okay? So this dot product over here, E dot dA, is E in the direction of ER dotted with dA in the direction of ER. So you've got EDA, and then you've got a unit vector dotted by itself is 1, okay? So this is EDA. All right, so now we can do the flux, the surface integral, okay? So this is surface integral, E dot dA. We just concluded this dot product is EDA. We also concluded the electric field is constant, so we can take it out of the integral, okay? So over the entire surface area. So we've got E, the integral over all the surface area, okay? And the surface area of a sphere is 4 pi r squared, right? So we have this integral is E times 4 pi times r squared. But from Gauss' law, this integral of the entire surface area equals 4 pi k times the charge enclosed. So let me use Q. Q is the charge of the solid sphere, okay? This is total charge of the sphere, of the charged sphere, okay? So this is the charge contained in this object over here. This is the charge contained over here, okay? Total charge included inside. All right, so from that, I have a formula for the electric field. The electric field is this 4 pi kq divided by 4 pi r squared, okay? So you see this goes away, you get kq over r squared, okay? And then of course we know the direction, so you can say the electric field is kq over r squared in the direction of the position vector, okay? Or you can say kq over r squared, and this is position vector divided by the radius. You can get kq r cubed, and then the position vector, okay? So we got a formula for the case where r is greater than the radius of the charged object, okay? Remember, the radius of this one is r. So this formula applies only if the point is outside the sphere, okay? So we just did one side of it. Now, next we're going to look at the electric field inside. Okay, case 2. Case 2, point inside the charge sphere, or R less than R. Okay, all right. So our point is inside. Let's say, maybe let me draw it again over here. So this is my charged sphere. I'm gonna make it bigger. Okay, this is a charged object. Let's say it's supposed to be charged everywhere. Now I'm trying to calculate the electric field inside. Okay, so my Gaussian surface is going to be a surface inside, like this. It's going to be my Gaussian surface. Okay, and let's say this is my R now, R less than R. All right, so the only difference from the previous one is that the Gaussian surface is inside into the charged sphere. You know what the difference is now? When the Gaussian surface is outside, the charge enclosed was the whole thing. But now, if you take this Gaussian surface, only a part of it is inside of it. So you're not going to include this charge over here. That's the difference. Do you see that? Okay. So basically, the basic difference is the amount of charge. So how do we do that? Well, first let's obtain the density. The density of the charge, this formula for density, right, is charge divided by volume, charge density, right? So that's total charge. We're talking about this object over here, the charged object, and the volume is 4/3 pi times radius cubed. This is the charge density, okay? How about the charge enclosed inside this Gaussian surface over here? It's going to be the density times its volume, okay? So charge enclosed in this case, charge enclosed is going to be the density times the volume of the Gaussian surface. Volume of Gaussian. Remember, the radius of the Gaussian surface is R now. I'm talking about this over here, R. So the density we have already did it is Q over 4/3 pi R cubed. But the density of, the volume of this Gaussian surface is 4/3 pi radius cubed. Do you see that? So the charge enclosed now is this one. You take the density, but now use the volume of this Gaussian surface, okay? So this goes away, 4/3 pi. So what you have is Q R cubed divided the radius of the object cubed. So this is the amount of charge enclosed inside. So for this case, this is our Q enclosed, okay? Otherwise, the symmetry conditions are the same, okay? The electric field is going to be constant everywhere. And the direction of the electric field also from symmetry is going to be in the direction of the position vector. So, so let's just say from symmetry is the same situation. We're going to say E equals E in the direction of position vector, where E is a constant on the surface, constant on the surface, okay? So this is our conclusion from symmetry. And we're going to this dot product and it's a spherical surface. So dA is also dA in the direction of ER. It's always the first spherical surface. The direction of the area is going to be the direction of the position vector, okay? So this becomes E in the direction of ER dotted with dA in the direction of ER, okay? So you just get E times dA, just like before, all right? ER dot ER is 1. A unit vector dotted by itself is 1, right? Okay. Now we go back to Gauss law. So this is Gauss law, right? Equals 4 pi k cubed. So this is the integral EdA we've said the electric field is constant over the entire surface. We can take it out. Okay, you get dA over here over the entire surface area. If you integrate dA over the entire surface area, you get surface area of the sphere, which is 4 pi r squared. Okay, so from the integral, you get this one, E times 4 pi r squared. But according to Gauss law, this equals 4 pi k times the charge enclosed. Okay, but now the charge enclosed is this one over here. Okay, Q r cubed divided by r cubed. So we're going to put that over here, Q r cubed divided by the radius of the charged object cubed. Okay, so the electric field is 4 pi k divided by this 4 pi r squared, and then you got this one, Q r cubed divided by r cubed. You see that? Now you see this r squared cancels r squared, just left only one r over here. Okay, first let me simplify this. This 4 pi goes away. So you got kqr divided by r cubed. So the electric field, the magnitude of the electric field is this one. You have k q r divided by the radius of the charged sphere cubed. Okay, and the vector is going to be k q r over r cubed in the direction of the position vector. This is if r is less than r. So you see, the electric field increases proportional to the radius inside. Okay, starts from 0 and then increase proportionally until you go to the surface. But once you get outside of the sphere, you remember the first formula? It drops as 1 over r squared, QQ, you see? So let me put them together. Let me put these two together. So this implies E equals, we got two branches. The other one was K, Q, r squared in the direction position vector if r is greater than the radius, or let's say put over here, r. And it's this one, K, Q, R over r cubed in the direction of ER if r is less than r. Okay, so you have two different formulas for inside and outside. So to give you some idea about how this electrics look like, let's put them in a graph. Okay, let's say this is the radius of the charged object. Okay, so this is inside, right? So at r, you see, you put r over here, you get kq r squared. So you get over here k q over r squared, but start from 0 and goes linearly to this point. This is inside. But once you are outside the sphere, the electric field decreases inversely proportional to the distance. It goes like this. Okay? So this is the electric field due to a solid charged sphere. Inside increases linearly, but outside drops inversely with the square of the distance. All right? So this is the electric field due to the solid sphere. Now we're going to look at electric field due to a uniformly charged spherical shell. Electric field due to a uniformly charged spherical shell. That means there's nothing inside. This is just a shell. Okay, so you have a sphere like this, but the charge is only outside. Okay, there's nothing. This is a shell. It's empty inside. All right, let the radius of this be r. Okay, so now we have two different situations. Outside and inside, the formulas are going to be different. Okay, so we're going to separate it into r greater than r and r less than r. Okay, case one, let's start with inside, which means R is less than R. Okay, so let's say I'm trying to find the electric field over here. So to take advantage of symmetry, because the spherical charge, I'm going to take a spherical Gaussian surface. Okay, so I take this. Can you guess what the electric field is going to be in this case? Huh? What do you think is the charge enclosed inside this Gaussian surface? There's nothing inside. The charges are all in the shell. So what's the charge inside over here? This is the charges. What do you say?
Negative?
No, the charges are over here. So what I'm saying is, what's the total charge enclosed inside this Gaussian surface?
0.
0, there's nothing. And because of that, the electric field is going to be 0 inside. But let's do it. So from symmetry, again, the same condition. This is spherical symmetry. So I'll just state it. So the electric field is E in the direction of ER, where E is constant on the surface. So this is my R over here, R less than R, okay? Where E is constant on the surface, okay? And for a spherical Gaussian surface, the area is always in the direction of position vector. dA is dA in the direction of ER, okay? So we get E dot dA would simply be E times dA, okay? Now let's go to Gauss law. So you've got this E vector over here, E dA, E is a constant times the integral of dA. That's 4 pi R squared times E. But what's the charge enclosed? Is 0. This equals 4 pi K, the charge enclosed inside, okay? But in this case, the charge enclosed is 0. There's no charge inside this Gaussian surface. The charges are on the shell, okay? So because of that, it follows that the electric field equals 0 inside or for R less than R. So inside this uniformly charged shell, the electric field is 0. No charge, no electric field inside, okay? Now let's do case 2. Case 2, outside, that is R greater than R, okay? So now I'm looking at the point somewhere, let's say over here. So again, let me put closer so that I can draw it. So I'm going to take a spherical surface to take advantage of spherical symmetry. That will make it unnecessarily difficult, okay? So I'm going to take this, and this is my R over here, okay? Again, this is spherical symmetry, so the same condition apply, okay? So the electric field is from symmetry, a spherical symmetry, the electric field is constant and the direction of the position vector, okay? Where E is constant on the surface, okay? That is, these are the conditions for spherical symmetry, all right? And of course, for a spherical surface, the direction of the area is in the direction of the position vector, okay? So E dot dA equals EDA, okay? So going back to Gauss law, E dot dA is EDA is a constant. You take this out, this is 4 pi R squared, okay? So this is my surface integral, E 4 pi R squared from Gauss law, that equals 4 pi K times the charge enclosed, okay? So let the charge on the shell be Q, okay? This charge over here, let this charge be Q. So that's the enclosed charge. This is my Gaussian surface. So all this charge from this shell are inside this Gaussian surface, okay? So that is my Q enclosed, okay? So let Q be the charge on the shell. The charge on the shell. So what that means is my Q enclosed is Q, okay? So this implies the Q enclosed is just Q, okay? So I get the following formula. E times 4 pi r squared. E times 4 pi r squared equals K, and 4 pi K, the charge on the shell, okay? And then you get this electric field is 4 pi KQ divided by 4 pi r squared, okay? So this goes away, you get KQ over r squared. And of course, we know the direction, so we can write the vector. It's KQ over r squared in the direction of ER, okay? So now let's put them together. E equals 0 if r is less than r, and equals KQ over r squared ER if the electric field is less than or equal to r, okay? So this is the electric field due to a uniform charged shell, okay? All right, now let's look at another kind of symmetry. So far we've been dealing with spherical symmetry. Now we're going to look electric field due to an infinitely long charged rod. Electric field due to, we take it to be infinite so that we can take advantage of symmetry, okay? Electric field due to an infinitely long, uniformly charged rod. Okay? So in this case, we have this rod over here. Okay, so we have charge over here. Okay, and we're saying it's infinitely long, so this goes forever in this direction, this goes forever in this direction. That is so that we can take advantage of symmetry, okay? All right, so first, what do you think would be the Gaussian surface that will help us take advantage of symmetry in this case? Now, first let's look at the conclusions from symmetry. Let's look at symmetry conclusions. Let me start over here. Symmetry conclusions. On what surface would you expect the electric field to be constant? You see, you would expect all the points at the same perpendicular distance from this rod.
So on the curved surface around the rod?
Yes, cylindrical surface, okay? If you have all the points at the perpendicular distance from the rod, you'd expect them to have the same electric field because they're subject to the same conditions, okay? So we expect the electric field to be constant on a spherical surface, cylindrical surface concentric with the rod, okay? That's conclusion from symmetry. So the first conclusion you can make is the electric field is constant on a cylindrical surface concentric with the rod. Concentric with the rod. The reason is because all the points are at the same distance, okay? Because all the points are the same perpendicular distance. All the points are at the same perpendicular distance. Okay? So that tells you the best Gaussian surface we can use in this case is a cylindrical surface. Okay? So let's take this surface over here for our Gaussian surface, like this. Okay? So this can be my Gaussian surface so that I can take advantage of symmetry because I know the electric field is going to be constant on this surface. All right. Now let's look at the direction. Okay. To find the electric field over here, what you have to do is you have to add up all the electric fields at all the points. Okay. If I take this charge over here, the electric field is going to be somewhere like this. But I can find another symmetric charge over here, which will cancel the component parallel to the surface. Okay. So this component over here will cancel out. So the direction will be in a direction perpendicular to the rod. Okay. So because of symmetry, the direction of the field is always going to be perpendicular to the rod. Okay. Take any charge over here, the electron goes this way, but I can find another charge on the other side that will go this way. I will cancel this component over here, and only the perpendicular component survives. Okay. So at any point over here, the direction of the electric field is perpendicular to the rod or perpendicular to the cylindrical surface. Okay. So that is conclusion from symmetry. So let me call this R perpendicular, which is the perpendicular distance between the rod and all the points on the cylinder. Okay. Now the direction of the electric field is in the direction of this vector. Okay. This is the the vector from the rod to the point, the perpendicular vector, and this electric field is in the direction of that vector. Okay. So we can say is in the direction of ER perpendicular. Okay. So let's say direction of the electric field is perpendicular to the rod everywhere. Perpendicular to the rod everywhere. Okay, because of symmetry. So we're saying the direction is, let's call this as E R perpendicular. Okay, is in the direction of, this means the direction is perpendicular to the rod, right? So what we're saying is the electric field is constant on this curved surface, okay? And the direction is always in the direction of R perpendicular, okay? So let's say the point over here is X, Y, Z, okay? Let's say this direction is the X axis, all right? What do you think would be this perpendicular vector would be? Now, if you take this point, you see, let's say my coordinate system is over here. So this position vector is going to be like this. Okay, it's going to be the sum of the x plus r perpendicular gives the position vector. Do you see that? This is my position vector. This is going to be the x coordinate, and then plus this perpendicular gives the position vector, right? So let me show you how to get this unit vector. So what we have is the position vector of any point is x in the I plus r perpendicular. Do you see that? This vector over here is this, the x coordinate, plus r perpendicular. Okay? But what is r? R is x in the I plus y in the j plus z in the k. Okay? So that tells you r perpendicular, you see this x in the I goes away, is y in the j plus z in the k. Do you see that? So this perpendicular vector over here is x in the j plus y in the k. And how do you calculate the unit vector? The unit vector would be r perpendicular divided by r perpendicular, okay? So it's going to be y in the I plus z in the k, and the magnitude r perpendicular will be square of y squared plus z squared, okay? So if you know a point, you can calculate the r perpendicular this way. It's everywhere on the surface. You got x on the x-axis, and every point over here is y in the j plus z in the k, all right? Anyway, so that's what we have right now. We're saying E, this is our conclusion from symmetry. E in the direction of R perpendicular, where E is a constant on the curved cylindrical surface on the curved cylindrical. That's our conclusion from symmetry. Okay, so now we're going to go to Gauss law. Maybe first let me find an expression for the enclosed charge. Okay, so what is my sphere? All right, so this is our perpendicular. Let the length of the cylinder be L. Okay, all right, okay. So let the charge density be lambda. Okay, let the charge density of the rod be lambda. Let the charge, because we're talking about infinite rod, so we have to talk about charge density be lambda. Okay, so if you take a length L like this, okay, the charge density is lambda times the length. Okay, this is linear charge density. You take a charge dq over here, you divide by dx, that's your charge density. Okay, now this is uniform, the density is constant everywhere, so the charge is going to be the charge density times the length. Okay, so this is the total enclosed charge. You take the charge density, you multiply by the length. You see, this is my Gaussian surface. So the charge inside is the charge of length L. Okay, so the total charge enclosed is this length L times the charge density of the rod. Do you see that? The length times the charge density gives you total charge enclosed. Okay, so that tells you charge enclosed is lambda times L. Charge enclosed is lambda times L. Okay, all right. Now let's go to the Gaussian law, Gauss law. This is the law. E dot dA equals 4 pi k times charge enclosed, which is lambda times L. This is my charge enclosed, right? Times lambda times L. That's what we have so far. So we just have to do this integral. But we're going to separate in 3 parts, okay? This cylinder has 3 different parts. We have this ends over here, you have the left end over here, and then you got the curved surface, okay? So I'm going to separate this integral in 3 parts. I'm going to say this E dot dA equals E dot dA on, so let's say left end, plus the integral of E dot dA on the right end. And then I'm going to say plus this on the curved surface. Okay, so that gives me total surface area. Now let's look at this end, on the left end. What's the direction of the area over here? You see, it's
Negative I.
negative I. Very good. But we just said the electric field is always perpendicular to the rod, right? So the dot product between the area and the field is 0 on the surface. Okay, so this over here equals 0 because the electric field is perpendicular to the area over there. The same thing for the right end. The right end, you see, the area is in the I direction, right? But the field is perpendicular to the rod from symmetry. So they're perpendicular to each other. Over here also is 0 because the area and the field are perpendicular to each other, okay? So we have also this one equals 0, the same reason, because E is perpendicular to A. So you just have to do this one on the curved surface, okay? So let's do this one first. Let's just say this equals E dA on the curved surface. The others are 0, all right? So what do we have? E is E in the direction of R perpendicular, where E is constant on this curved surface, okay? Which means I can take it out. The area is also in the direction of R perpendicular. It's dA in the direction of R perpendicular, in the direction perpendicular to the rod. Okay, so that tells you the dot product E dot dA is E in the direction perpendicular to the rod, dotted with the area element in a direction perpendicular to the rod. Okay, so the dot product in these two unit vectors is 1, so you simply get EDA. All right, so this on the curved surface, E dot dA on the curved surface is simply the integral of EDA on the curved surface. Okay, but remember we have already concluded the electric field is constant on the curved surface, right? We're doing the surface integral on the curved surface, so we can take E out. So this is E times dA, and this is curved surface. Okay, so this is area of the curved surface. This over here is area of the curved surface. Can you tell me what's the area of the curved surface?
2 pi r times length.
Very good, 2 pi r times length. So this equals E times 2 pi. Remember our radius are perpendicular, okay, times length. All right, that equals, according to Gauss law, 4 pi k times the charge enclosed, which in this case is charge density times the length. Do you see that? You see, this is my surface integral, and from Gauss law, that equals 4 pi k times the charge enclosed. The charge enclosed is the charge density of the rod times the length of the rod, okay? So you get the following for the electric field. So this is 4 pi k times lambda L divided by 2 pi r perpendicular times L, okay? So you see L goes out, and then you get 2 from here. So you just get 2k lambda divided by r perpendicular, okay? So you just have charge density and decreasing inversely with the perpendicular distance, okay? And of course, we know the direction is in the direction of perpendicular to the rod. And so that gives us the electric field is 2k lambda over the perpendicular distance of the radius of the sphere in the direction perpendicular to the rod. Okay, so that is how you calculate the electric field due to a linearly charged, which is assumed to be infinitely long in all directions. Okay. All right. Next, we're going to look at electric field due to a uniform charged plane that extends infinitely in all directions. The reason we're assuming that it extends infinitely so that we can take advantage of symmetry, okay? If something extends in infinite directions, you can take any point to be the midpoint, okay? That's the advantage. You can treat every point as a midpoint if something extends infinitely. So that's why we're assuming that they extend infinitely so that we can take advantage of symmetry. So let's look at electric field. Electric field due to a uniformly charged plane, a uniformly charged plane that extends to infinity in all directions, that extends to infinity in all directions. Okay, so that's what we have. This plane over here extends to infinity in all directions, okay, and is uniformly charged. Uniform charged. All right, so we're going to get an expression for the electric field due to this plane. Okay. First, we have to look at symmetry conclusions. Symmetry conclusions. Now, if you take a certain point, how would I put this? Anyway, if you take a certain point in front of the plane, you know, let me see. So if you take a certain point from the plane, you see if there's another point at the top, there'll be another symmetric point at the bottom to eliminate the electric field parallel to the plane. Okay. Let me see. I can show you my hand. Okay. If I have a point over here, you see, electric field from here. If I find electric field from the top, there'll be another point at the bottom to eliminate the component parallel to the plane. So only the component perpendicular to the plane will survive. Okay. So you take a certain point in front of the plane. Let me take the point over here. Okay. I'm not going to throwing, but let's say you take the field is this one over here, or be somewhere over here. I can take another point from here, which will be in this direction over here. So you see these components will cancel each other, and only the perpendicular component will survive. Okay, give me any point, I can find another point that cancels the component parallel to the plane. Okay, so it's only the component that's perpendicular to the plane that's going to survive. Okay, so one of the conclusions I can make is that the direction of the electric field is perpendicular to the plane everywhere. Direction of the field is perpendicular to the plane everywhere. Okay, let's say this is in the, if this is in the xz plane, the direction will be j. Okay, if it's in the xy plane, the direction will be in the k, and so on. Okay, will always be perpendicular to the surface. And remember, this is positively charged. If the direction over here is the I direction, on the other side, it's going to be negative I. It's going to be repulsion. Okay, so if you have this plane, if it's this way over here, it's going to also be this way over here. If it's I over here, it's going to be negative on the other side, okay, because it's repulsion, okay? So if it is I over here, it will be negative I on the other side. All right, and the other thing we can conclude from symmetry is at every point parallel to the plane from symmetry, the electric field will be constant, okay? Actually, we'll see that it's going to be constant everywhere. But from symmetry, let's say at any point parallel to the plane, from symmetry, you can assume the electric field to be constant, okay? So the electric field is constant on a plane parallel to the plane, on a plane parallel to the plane. Okay, so the direction is going to be a constant, and let's call the direction of the perpendicular to the plane to be maybe EA. That's the direction of the area. The direction of the electric field is going to be in the direction of the area. Okay. Well, on the other side will be the negative direction of the area, but let's say it's E in the direction of EA. Okay. So now, how do we select our Gaussian surface now to take advantage of this? Let me draw my Gaussian surface first. So our suitable Gaussian surface is going to be a cylinder like this. Then we have this. Okay, we're going to take, and then you have this cylinder crossing the surface. Does it make sense? I'm not even drawing, but you've got, that's my Gaussian surface. You got the plane, and you've got a cylinder passing through it. Okay, small cylinder. Okay, that's what I'm trying to do. All right. So we want to obtain the electric field. Is this one. Okay, so we're against Gauss law. Okay, what does Gauss law says? This E dot dA equals 4 pi k times the charge enclosed. Okay, so let's say the area of this one, let's call this the area of this one is dA. Okay, let the charge density be sigma. Charge density is uniform, so it's just charge is going to be constant. Okay, so this is the charge density of the cylinder. Okay, so what's the charge enclosed? This is the only part of the charge that's enclosed, right? So can you tell me what's the enclosed charge? The charge density is sigma. The area of this one is dA. So what's the charge enclosed? The charge density times this area, right? The charge enclosed is the charge density times this area. That's the only area enclosed by this Gaussian surface. Okay, so in this case, Q enclosed is the charge density times the area enclosed, dA. Okay, all right. So I have the following now. This surface integral over here equals 4 pi k times the charge density and times the area dA over here I'm talking about. Okay, so I'm going to divide this in three parts. I've got this surface, left end, right end, and curved surface. Okay, so let's do that. So this integral on the closed surface, E dot dA, we're going to separate in three parts. E dot dA on the left end plus E dot dA on the right end, and then plus E dot dA on the curved surface. Okay, let's start with the curved surface. Can you tell me what the direction of the area on the curved surface is? You see, it's going to be parallel to the plane. On the curved surface, the direction is always perpendicular to the axis of the cylinder, right? So the electric field we have concluded is in this direction over here, is in this direction over here, the electric field, right? But the area over here is parallel to the plane, okay? So on the curved surface, the electric field and the area are perpendicular to each other, okay? So the flux is going to be zero on the curved surface. Over here, it's going to be zero. The reason is because the electric field is perpendicular to the area on the curved surface. Do you see that? Okay, so we have only this to left. So now let's look at this over here. What's the direction of the area over here? Is it perpendicular to the plane or parallel to the plane? Remember, the direction of the area is perpendicular to the area, right? So it's going to be parallel to the field. You see that? The field is this way. The direction of this area also can be parallel to it because this plane over here is parallel to this one, okay? So on the left end, it's going to be, let me do them separate maybe. This E dot dA, left end, okay? This is in the direction of the area. They're both in the same direction. And this is dA in the direction of the area. There was parallel, so you just get EDA. And E is a constant, okay? The same thing for the right end. E dot dA over the right end. You see, if this is positively charged, it's going to push in this way in this direction and this way in this direction, okay? Was the direction of this area over here the same? It's the direction of the area, right? The direction of the area is in this direction of the electric field. So the same thing for this one too. So this one is also EDA. Okay? So this is zero, this is EDA, this is EDA. So the total is twice of this from the left end and from the right end. Okay? And so that we equate it to this one. This is our enclosed charge, okay? Sigma charges times dA is our total charge. So this equals 4 pi k times total charge enclosed, which is charge density times the area enclosed. Okay, that's it. So we have the electric field equals 4 pi k times the charge enclosed, this one over here, and then divided by this one, by 2 dA, okay, by 2 dA, all right? So divided by 2 dA. So you see, dA cancels out, this cancels out, 2. So the electric field is 2 pi k sigma. That's it, 2 pi k sigma. Let's write in terms of epsilon, okay? What is epsilon? Epsilon is 1 over 4 pi k, okay? Or 4 pi k equals 1 over epsilon. So 2 pi k equals 1 over epsilon. So you can write one also as sigma divided by 2 epsilon, all right? So you see it's a constant everywhere. It doesn't even depend on distance. If you've got a uniform charged plane that extends everywhere, the electric field is a constant everywhere in space. This is a constant, this is a number, it's a constant everywhere. And its direction is in the direction of the plane, perpendicular to the plane, okay? So you can say this is 2 epsilon in the direction of EA. Of course, it will be A in one side, it will be negative EA on the other side, okay? So if you've got a uniformly charged plane, the field is constant everywhere, all right? It doesn't even depend on the distance. Do you have any questions so far? No. Okay, let me look at my last section. Conductors in electrostatic equilibrium, okay? Conductors in electrostatic equilibrium. Conductors in electrostatic equilibrium. As you remember, conductors are substances with free charge or free electrons, right? So what we call conductors in electrostatic equilibrium are conductors where the free charges or the valence charges are at rest, they are moving, okay? These are conductors where the free charges are not moving. The free charges are at rest. Okay? So let's look at some properties of this kind of conductor. So let's say this is a conductor over here. We're saying the charges are not moving. Why are they not moving? If there is electric field, will they move? What is force? Force is charge times electric field, right? So we're saying they're not moving. We're saying the force acting on them is 0, right? That's what they're not moving means. There is no force acting on them, okay? But this force over here equals charge times electric field, right? So what does it tell you about the electric field inside? The electric field inside is 0 everywhere, okay? No force at rest means the net force acting on them is 0. But the force is charge times electric field. So the force is 0, the electric field is 0. So one of the conclusions we can make is the electric field inside is 0 everywhere. The electric field inside is 0 everywhere. Okay, so that's one conclusion. The electric field equals 0 inside. Now let's try to find out whether there are charges inside this conductor or not, okay? So we're going to use Gaussian law. Let's take a Gaussian surface, arbitrary Gaussian surface over here. Okay. And as you know, Gauss law says if you do this on the Gaussian surface, E dot dA, you get 4 pi k times the charge enclosed, right? So what do you think is this integral in this case? The electric field is zero everywhere, right? So if the electric field is zero, what do you think this integral is?
0.
Zero. This is zero. And so that tells you the charge enclosed is zero, right? So this implies the enclosed charges is zero. So the conclusion is there are no charges inside. The charge can only be found on the surface. There are no excess charges inside. Excess charge can only be found on the surface of the conductor. So the conclusion over here is there are no excess charges. There are no excess charges inside the conductor. Inside the conductor. Excess charges can only be found on the surface. Excess charges can only be located on the surface. Okay, so for this kind of conductor, if you've got charges, they should be on the surface. They cannot be inside. Okay, they should be distributed over here. No excess charges inside a conductor in electrostatic equilibrium. Okay, okay, now the charges are on the surface. Now let's look at the electric field over here. These charges are not moving. Okay, they're not moving parallel to the surface. Okay, so can we have electric field which is parallel to the surface over here? If there is a component of electric field that's parallel to the surface, this charge should be moving, but they're not moving. So that tells you the electric field just outside can only be perpendicular to the surface. Because if this has a component in this direction, this charge should be moving, but they're not moving. So the electric field just outside cannot have a component parallel to the surface, okay? Because these charges are not moving. So the conclusion is the electric field just outside a conductor is perpendicular to the surface of the conductor, okay? So that's another conclusion we can make. The electric field just outside, the electric field just outside cannot have a component parallel to the surface because the charges are not moving to the surface because the charges are not moving. Okay, if there was, the charges would be moving. Okay, so the conclusion is the electric field just outside the conductor is perpendicular to the surface. So the conclusion is the electric field just outside is perpendicular to the surface. Okay, so the electric field inside is zero and the electric outside is perpendicular to the surface everywhere. Okay, it cannot have a tangential component. All right. Okay. Now we can obtain expression for this electric field just outside using Gauss law. Okay. Let's take this Gauss law over here. We're going to take this cylindrical surface over here. Okay. Let the charge density be sigma. Okay. Let's say this area over here is dA. So if the charge density on the surface is sigma, the charge enclosed over here would be sigma times dA. Okay. So if I use this cylinder, first let me say, let the charge density on the surface be sigma. Let the charge density be sigma. In this case, it is not constant. It changes from place to place. That's why I'm taking a very small cylinder so that I can assume the density to be constant, okay? So this implies, you see, the charge enclosed in this Gaussian surface over here is the charge density times the charges on the surface over here, right? If the area is dA, the charge enclosed will be dA times the charge density, right? So I have Q enclosed is sigma times dA, okay? Now let's calculate the surface integral or the flux. You see over here, the electric field 0, no contribution over here. Do you see that? On this surface over here, the electric field is parallel to the curved surface, but the direction of the curved surface is perpendicular, right? So on the curved surface, the electric field and the area are perpendicular, no contribution. The only contribution comes from here. It's over here, the electric field is 0. On the curved surface, the field and the area perpendicular, no contribution. We have only contribution from this one, okay? And that is the electric field times dA. We don't even have to integrate. This is a very small area element, dA, okay? So in this case, what we have is this one, dA over here, is simply E times dA, okay? I'm taking a very small cylinder of area dA because the charge is not a constant, okay? So that's why I'm taking very small area element. And that is 4 pi k times the charge enclosed, which is sigma times dA, okay? So dA cancels out. You get the electric field is 4 pi k times the charge density. And remember, 4 pi k is 1 over epsilon, okay, if you prefer that. So the electric field on the surface is proportional to the charge density, okay? But remember, the electric field depends on the curvature. You remember we did electric field due to a solid charge or due to a shell charge. The electric field looks something like this for a shell charge, kq over r squared, where r is the radius of curvature. The electric field is inversely proportional to the curvature on the surface, okay? So that means the smaller the curvature, which means the sharper the surface, the greater the charge density, okay? So the electric field increases with sharpness of the surface, increases with sharpness as 1 over r squared, where r is radius of curvature. Okay, this is radius of curvature. But the electric field is proportional to charge density according to this formula, right? So that tells you the charge density is greater on sharp edges and smaller on dull edges, okay? So the sharper the curvature of the surface or the edge, the greater the electric field. So charge density is greater on the sharper edges, than on the dull edges, okay? That's why you have to get away from sharp objects during lightning, okay? The electric field is the greatest on sharp edges, okay? So you have to get away from very sharp objects during lightning because the electric field is the greatest on sharp edges. So the duller the surface, the smaller the electric field, the greater, the sharper the surface, the greater the charge density. All right. Do you have any questions? All right, then I'll see you on Tuesday. And remember, that is a test day. Okay, we're going to take this on chapters 1 through 4. Okay, so see you on